Okay, let me start. Today we're going to talk about the recurrent neural network. So comparing to the convolutional neural network that we discussed so far, the recurrent neural network enables us to deal with the sequence data than the one frame or the one samples among the training data set. So let's see the detail. Why we need to deal with the sequence data? So there are several kinds of the application that need to deal with the sequence data. The first one is the speech recognition. So the goal of the speech recognition something like this. So this is the xn or our input data, such as something like the audio form, that we want to extract the semantic meaning or from the semantic sentence from this audio signal. So this is the speech recognition things. So in this case, it is one sample is xn, something like our previous examples, but in this case, this xn is related to the previous sample. So we need to deal with this sequence data rather than only considering this one sample. So this is the why we need to deal with the sequence data. Another thing is that in the music generation thing, from the one signal or the one input, we want to generate the new image, new music from this one sample. So this is the one example. The sentiment classification is that from the sentence. Actually, this is like the reply on the website that you want to extract the sentiment or the emotion from this natural language, something like this. So in this case, you need to analyze this sentence, which was the sequence data. What else? So DNA sequence analysis, something like this, or the machine translation from the one sentence from the other language. We want to transform this language to our new language, right? Or what else? The video activity recognition. So if you have the video sequence with some kind of the stack of image, we want to extract the semantic meaning from this video, something like the learning. So in this case, you don't understand the semantic meaning from just one image, but you need to see the several kinds of sequence to understand the meaning of this video set. What else? The name entity recognition. So for this kind of the sentence, you want to find the name entity from this sentence to something like this, right? So to do this, you need to understand this sequence data set, right? And then except for this kinds of application, there are so many kinds of application you have to think about the sequence data. So in this case, if you just use the convolution neural network, you don't have any way to use the previous signal to increase the performance. So in this case, we need a good another way to deal with the sequence data set. So that's why we introduced the neural network, recurrent neural network. Before that, let's think about the vanilla convolution neural network. Vanilla means just like the basics, right? Basic convolution neural network or the Bayesian neural network. The architecture of the Bayesian neural network, something like this, right? Let's say this is the xn input signal, then this is output signal, might be some approximated version of the yn. Then there are several kinds of stacked layer among them, right? So this is the vanilla neural network. Comparing to this one, the recurrent neural network is shape of the recurrent neural network is something like this, right? For example, in some case, if we have just one input, okay, in this case, let's use the xt. T means some kind of the order of the sequence, right? In some case, from the one samples, we want to make a sequence. Let's say yt plus 1, yt plus 2, something like this. So for example, if you think about the image captioning that generate the sequence of the word from the image, we need to the one-to-many case. We want to consider the one-to-many case, right? Another case, if you think of the action prediction, the input was the sequence of the video frame, something like xt minus 1, xt plus t minus 2. Then we want to find out action class yt from this kind of the previous images. So in this case, we need to consider the many to one case, right? What else? So when you think of the image, video captioning, something like that. So this is the one frame, this is another frame, this is the another frame here. Then we want to make a caption, which was a sequence data set, right? Like yt plus 1, yt plus 2, something like this. So in this case, this is the many-to-many case, right? So in this case, we also need some kind of a way to consider the previous data set, previous sequence, to find out the output by using the previous information, right? So this is the another example of the recurrent neural network. Finally, in some case, we want to estimate the output of the input xn, but in another samples, we want to consider the previous estimation to improve this one, right? And xt plus 2 case and yt plus 2 case, we want to use the previous signal to improve this estimation, right? So this is the many-to-many case. For example, if you think about the video classification on frame level, we have to think about the many-to-many case, right? So to summarize, there are several kinds of scenario we have to think about the sequence data processing. So this is the general case of the recurrent neural network. So specifically, compare it to the vanilla neural network. So let's draw here. So here from xn, there is a TNN, right? Deep neural network, just deep neural network, and y put here, right? It was the general form of the neural network, right? The recurrent neural network has this arrow. So what does it mean? So the key idea of the neural network, a recurrent neural network, is that RNN recurrent neural network have an internal state that is updated as a sequence is processed. So rather than using this deep neural network for each sample, which is independently sampled from your training data set, in recurrent neural network, we need to see the interdependency between the sequence. So we need some way, something like the internal state, to use the previous information to estimate the output of the previous current input, right? So this is the concept of the recurrent neural network. Actually, it is really hard to understand this recurrent term, right? So we need to unfold this recurrent neural network, something like this, right? So it might be easier to understand. So in here, the one RNN unit can be used another sequence here, but these two RNN units are connected to each other, right? Something like this, right? So this is the previous samples with the previous output, and this is the current input and current output. To estimate the current output, we can use the previous information by using the connection here, right? And then to estimate this output of this input, we can use the another connection from here, something like this, right? Something like by using the sequence input with the sequence output with the connected one here, we can improve the sequence data processing using the recurrent neural network. Okay, so this is the general idea of the recurrent neural network. So the question is, how can we convert the information from the previous sequence? Then how can we estimate our current output by using the previous information, right? So this is the design of the recurrent neural network. Okay, so let's see the detail. Okay, when you think about the one recurrent neural network module, it consisting of it has some state concept. So let's think about this. So let's say this is the input at t frame or t time step. Then in the recurrent neural network, there are some module defined something like this. So this is the current timestamp, and this is the ht minus 1 is the old state, something like from here, right? With some kind of function, with parameter w, then we can generate the new state, which will be used the next time step, right? So by formulating this one, we can process the sequence of the vector x by applying the recurrent formula at every time step, right? So this is the recurrent neural network. So training the recurrent neural network means we want to find out the parameter w within the recurrent neural network. Okay, so let's think about how can we train this one. But anyway, by using this additional concept, we can deal with the sequence data set, right? So notice that the same function and the same set of the parameter are used at every time step, right? So in other words, okay, if we think about the sequence data set, okay, let's say this is xt, t minus 1, t plus t minus 2, yt minus 2, yt minus 1, yt, let's say t plus t, large t plus large t here. Then by introducing the new hidden state h here, we can estimate the output yt minus 1 by using the h0 and xt minus 2, something like this, right? And then to estimate this one, we can use this signal and this signal, something like this, right? And to estimate this one, we can use this, something like this, right? So this is the general concept of the recurrent neural network, right? This is very intuitive, isn't it? And let's see in detail of the recurrent neural network. Okay, so So in here, within the recurrent neural network, we need to some kind of way to deal with the internal state H. So we've discussed the internal state is updated by using the current input with the trained parameter W, right? Then if you think about the detailed model of this one, it can be generalized something like this, right? So HT is the weighted with some parameter with the previous statement here, and another network parameter with the current input here with some kind of nonlinear function, then you can update HT, something like this. And then to generate the output yn from this hidden state, we need another network parameter why with this ht here. Then we can generate the yt here, right? So if we draw this one within the figure, it would be something like this. So t minus 1 here, xt here, right? So this is the whh, this is the wxh, and then this is summation, right? With the tangent here, and it will be the new ht, right? Then yn will be the another why, and it will be the yt, right? So this is just one block within RNN module, right? So here there are three kinds of the trainable parameter. So first one is whh, second one is the wxh, and why, right? So because this is just a tangent module, nonlinear function module, this is just the summation, element-wise summation module. So this is just one module of the recurrent neural network. So comparing to the CNN, just CNN, something like xt, wt, and yt. So comparing to the previous CNN with the hidden state module, we can consider the previous sequence, the information from the previous sequence by using this hidden state, right? So this is the general concept of the RNN compared to CNN, right? So similar to the convolutional neural network, recurrent neural network also have the computation graph concept. Why we need to the computation graph? Why we need to understand the computation graph? To train our convolutional neural network, our neural network, by using some kind of backpropagation concept, right? So okay, so let's say there are sequence here and hidden state here. So by using the one RNN module, define the FW. So W means something like this one, three kinds of network parameter, right? Then we can generate the new state H1 with another output here, right? And then in this timestamp, with the input signal and the hidden state here, we can process another hidden state here with another network output here, right? So this is the computational graph, which is the recursively processed from first state to the last state. So this first and last state defined with the number of the number of the element within the sequence, right? So this is the computational graph. So interestingly, in this recursively used module, we need to use the same weight at every timestamp. So it means that each module have the shared network parameter W here. So it means that when training this recurrent neural network, this network parameter should be updated simultaneously across the every sequence, right? So this is the one particular thing. So comparing to the convolutional neural network, which is also use the same network parameter for every element within the sequence, but comparing to the convolutional neural network, RNN also use the same network parameter, but they are connected with the hidden state, something like this, right? So this is the difference between RNN and CNN, right? So we can compute this computational graph for the several kinds of the RNN cases. The first one was the many-to-many case, right? So let's think about the many-to-many case. So based on this kind of the computation graph from the RNN network, so from the sequence of data x1 through the xn through the xt, with the hidden state h1 through the ht, with the shared network f of w, right? Then we can generate the several kinds of the output sequence. So first case was the many-to-many case, right? What was that? So we want to generate the output yn according to the xn, right? y2 with the x2, yt from the xt, right? So in this case, we can make the computational graph something like this with the shared network fw with the hidden state h1, h0, h1, h2 through the hp, right? So this is just one case for the many-to-many case, right? Another case is the many-to-one case, right? So from the sequence data, we want to generate the one output from the sequence data, right? So with the shared network fw, we can generate the one output from the many sequence data set. What else? The one-to-many case from the one input signal with the several kinds of the network with the shared parameter w, we want to generate the y1, y2 through the yp, right? So this is the case of the one-to-many case. So actually, those kinds of the case of the recurrent neural network have the some kinds of the variant, but with this computation graph, we can easily train this recurrent neural network with some kinds of the backpropagation concept, which we discussed previously, right? So comparing to the previous one, the main difference with the convolutional neural network, those kinds of the network at each time step are connected, right? So it means that when backpropagating our loss signal to each network parameter w, they are updated. They should be updated simultaneously. We will discuss this later, but yeah, let's think about the computation graph first, and then another case is that the sequence to sequence case. So sequence case mean, okay, we have the input sequence, something like this, and we want to make an output sequence, right? So let's say let's think about the machine translation, something like this. Let's say which yeah, let's think about that. Okay. 있습니다. This is Korea, right? And we want to generate the English, right? There is the do, right? Then the each word in Korean can be the sequence at one timestamp, right? Then output of each word in English will be the YT or YN, right? So this is the sequence to sequence case in the machine translation. So to solve this problem, the many to one with the one to many will be used. So first of all, by using the many to one RNN network, something like the encode the input sequence into a single vector, as we discussed here, right? And then decode this output sequence from this input this statement from the input produce output sequence from the input single vector. So we can generate the output sequence using some kinds of this network, right? So by simultaneously use the many to one and one to many recurrent neural network, we can deal with the sequence to sequence case. Actually, this concept was solved in the sequence to sequence learning with the neural network paper published in New Reefs to 2014, right? Actually, it was the state of art for the machine translation field, but nowadays there are popular way to solve the machine translation by using the transformer concept, so which will be discussed later in this lecture. But this is the just one example using the recurrent neural network. Okay, so how can I train this one? How can I train this one? So train this neural network. What's the meaning of the training this neural network? What's the meaning of this training? We have to train. We have to find out network parameter W1 here, W2 here. So it's not a shared, but because the specific parameters will be different, but we have to train this W1 and W2. Okay, let's say W1 and W2, or in this case W encoder, W decoder, because we generally we say that the left hand side is the encoder, right hand side is decoder, right? Anyway, so we have to find out this network parameter W, right? Then how can I find that? We need to compute the gradient of the loss signal according to each parameter W, right? Okay, let's do that. So first of all, given sequence data x1 through the xt, large T means the number of word or number of element in the sequence. Then we can generate the output, right? Something like this, right? It might be the many to one or the one to many or the many to many. In this case, this is many to manys, but we can just to think about the general case of as a many to many case, right? So from this kind of output, we can define the loss function, right? Loss function, right? So for example, regression loss or the classification loss, something like this, right? So when we define the loss function, we can backpropagate the last loss function to the input signal x. So how can we do that? In the forward propagation step, we can forward the output, something like this, right? Something like this. And the backpropagation step, this red arrow is the backpropagation. Backpropagation step. Each loss gradient will be backpropagated. So through this computation graph, so something like this, right? Something like this, right? Something like this. So especially when you think about training this RNN network with the parameter W, the loss gradient is a two-way, right? The first loss gradient from here, the second loss gradient from here, right? Right? So this parameter, the loss gradient of this W parameter should be added from this first gradient and second gradient, right? What about this? What about this W? There is also first gradient and second gradient. But interestingly, these two network parameters should be shared, right? So it means that to update this parameter W across every timestamp, we have to forward every sequence and backpropagate every sequence again. So it might be very time consuming when we think about the very large scale sequence, right? So it's not an efficient way. So we need another way to train this network W, right? So in here, we can think about truncated backpropagation through the time. So what does it mean? So comparing to this one, considering the every possible forward and every possible backward case, we can just run forward and backward through the chunk of the sequence instead of whole sequence. So instead of a whole sequence, we can think about just chunk of sequence or the subset of a sequence, and then we can compute the forward and backward propagation with a loss function, right? And then after that, we can use another chunk of the signal sequence or the words, right? And carry the hidden state from here. We need to use this hidden state from the previous one, but only backpropagate with some smaller number of steps. So what does it mean? Rather than backpropagate this signal to here, we don't consider this one, but just update within this chunk of signal, right? Something like this, right? In another step, by only using this part, we just backpropagate this loss function to this one, and this one without this one, right? So to summarize, by forwarding for each chunk, we update each chunk per each step, something like this, right? So this is the truncated backpropagation through the time. So to train the neural network, we can use this kind of the way to train our recurrent neural network stably and efficiently. Okay. So to summarize, the recurrent neural network have some kinds of trade-off, such as advantage and disadvantage. So first advantage is we can process any length of the input, right? So because if we just define the one RNN module or the one RNN unit, then by unfolding this RNN module, we can deal with infinitely many lengths input in theory, right? And the computation for each step T can, in theory, use the information from many steps back, right? So when we considering this input and output signal, we can use the information from the previous one because they are connected each other. So we can use the information from the many steps back. But please remember, this is the theory. Actually, in practice, it's not, because we will discuss this problem later, but there is some kind of problem called the vanishing gradient problem. So actually, the RNN is not good way to considering the many steps back. You can just considering the near previous the hidden state, something like the 1 frame or 2 frame, or the 1 step or 2 steps. So we need another way to considering the many steps back. Okay, so we will discuss in the next slide. But yeah, in theory, yeah, this is theory. And model size does not increase for the longer input, right? Because we need to define just a single unit, right? For any length input. And what else? Same weight applied to every timestamp, right? So there is a symmetry in how inputs are processed, right? Because every steps use the shared RNN network, so we can guess which network input can be processed with our RNN module to output dataset. Output, right? So this is the advantage of the RNN network. But there is some limitation or the disadvantage. The first one is recurrent computation is slow, right? Recurrent computation is very slow. Why? Because to train this network, we have to use the forward and backward step for this very large scale computation graph, right? In practice, difficult to access the information from many steps back that I discussed previously, right? So we need to find out the way to solve this limitation, because this is the main limitation of the recurrent neural network. Okay, let's see the why. Okay. To summarize, the recurrent neural network can be defined something like this. So from the xt input of the t frame or t timestamp with the previous hidden state ht-1, then by stacking these two input with some network parameter w, and by using this nonlinear function, we can generate the new hidden state with the output, right? If we formulate this one as an equation, it will be something like this, right? So from previous hidden state here with the xt input xt, right? With the network parameter w. Okay, let's use different color, right? Then with the tangent function here, it can be formulated something like this, right? If we rewrite this term as a matrix multiplication term, something like this, right? This is very easy. Then we can say that w is equal to here with the parameter here, right? With the tangent function. With the tangent function, we can generate a new ht, right? Right? So this is just one node for the recurrent neural network, right? So what I want to do? To train this network parameter, we can think about the loss gradient with respect to the yt, right? So to this end, we need to compute the loss gradient with respect to xt, loss gradient with respect to the ht-1 w loss, right? So by using this loss gradient, we can update or train this network parameter w, right? So to this end, what can we do? We need to compute the local gradient to use the chain rule, right? So similar to the convolution neural network, right? So, for example, the backpropagation from h to ht to the ht minus 1 by using the some kinds of the signal or the gradient from here, right? Okay, so let's think about this one in detail. So to compute this one, because this ht, hl, ht minus 1, l here, to derive this from ht, ht, l, ht minus 1, ht. We already know this one from here, so we have to know this one, right? To use the chain rule, right? Then, because we already have the equation ht with the ht minus 1 here, we can compute the gradient of ht over ht minus 1, right? Then how can you do that? You can just to find out gradient, this one, with respect to the ht minus 1, right? If you do some kind of practice to this gradient derivation, you can easily formulate this one from this one. So please do derive this one. So anyway, so ht over ht minus 1 can be computed this one, right? Because this is a tangent function, so this is a tangent gradient. Okay, so because this one RNN unit is connected as a sequence, something like this, right? Then let's think about the loss gradient from here to here, right? So to compute this one, from the loss gradient over the gradient w, this w, right? So it can be computed by chain rule, right? So this is it can be extended something like this, right? Something like this, right? From this step to the here, right? Right? So in here we can merge this term at here, and finally there is the step here. So from this one and this one, no. From this w and h1, we can easily compute the gradient of h1 over according to the gradient parameter w, and we can also compute this one. So the only thing we have to compute this one, so this internal backpropagation step, right? But we already compute this one, right? What was that? Here, right? Here. So by subtracting the previous gradient onto here, we can compute the loss gradient with respect to the network parameter w, right? So by using this w, we can train or update network parameter w, right? Network parameter w, right? So what else? So interestingly, this one from this one, right? This one is almost always less than 1. Almost always less than 1. Why? because the shape of the tangent gradient is something like this. So right, so in this case it's almost always the less than 1, so it means that will be the vanishing gradient problem. So what is the vanishing gradient problem? We want to backpropagate this gradient to follow the line to here, right? By using this one, right? So from here to here, right? But in the internal case, this term is almost always less than 1, so it will be less than 1. Let's think about 0.1 times 0.1 times 0.0.1 will be something like 1, right? So it is really small value, so it might be removing the loss gradient to this one. So this is just called of the vanishing gradient problem, which is really critical problem to train your neural network. So actually, because RNN has this kind of similar problems, so it is really hard to train. So we need another way to solve this limitation. But yeah, this is the limitation of the recurrent neural network, right? So to solve this problem, there are another way to improve the loss gradient, vanishing gradient problem, just called the LSTM, called the long short term memory. So here's things. It was the vanilla RNN or the basic RNN. So if you remember the formulation of the RNN here, it was something like this. So input signal X with the internal state H with the runnable parameter W with the nonlinear function tangent and output HT. Right? So with this HT, we can generate the YT. We can generate the YT from HT, right? Similarly, in the LSTM, we can generate the next hidden state HT from the XT, input signal XT, and previous hidden state YT, right? But comparing to the original RNN, there is another module called the CT. This is the cell state. This is a cell state to adjust this hidden state with this term to overcome the vanishing gradient problem, right? So actually, this is very complicating because there are W here, some nonlinear function here with some kind of the multiplication term with the nonlinear function here. But by using this complicating method, we can improve the vanishing gradient problem from the recurrent neural network. Okay, so this is called the LSTM. Let's see the detail from this page, right? Actually, to summarize, you don't need to remember everything within the LSTM. Actually, it's not possible because in real case or in practice, you can just use this LSTM module as something like the Lego, right? But at the first time, you need to try to understand what's going on within this LSTM, and then think about how can we use this kind of the LSTM module for your recurrent sequence processing application. Okay, so comparing to the this one, please remember this RNN module, LSTM module, something like this. It looks really complicating, right? So, but the idea is very simple. The LSTM introduced the new CT variable. This is called cell state. When HT was the hidden state, right? And there are three gate function. So F, I, G, O. Okay, so let's think about each role first. Okay, so if you just see this one, this part, this is just the RNN module, right? This is just RNN module. But in the LSTM module, there are several kinds of the nonlinear function here to deal with the to decide which one should be remembered, which one should be forwarded, or which one should be erased, or which one should be discarded, right? So these gate functions determine this kinds of concept. Okay, so let's see the detail.